this session, you will be able to determine the concentration of the solution being titrated. Please prepare your pen and your worksheet booklet while watching this video. Please open up your booklet at worksheet 10 to solve extra exercise about Jebel water. Jebel water is a basic solution constituted of an equimolar mixture of hypochlorite and sodium, so Na plus and ClO minus, with sodium chloride, which is Na plus and Cl minus. Jebel water is obtained by the action of chlorine gas on sodium hydroxide solution according to the equation of reaction 1. So reaction 1, it is the reaction of preparation of Jebel water. Cl2, which is a chlorine gas, it reacts with OH minus coming from the sodium hydroxide to give a mixture of ClO minus, Cl minus and H2O, which represent the composition of Jebel water. In addition to ClO minus, Jebel water contains Cl minus, Na plus and H2O. In an acidic medium, Jebel water reacts according to the equation of reaction 2. So, if Jebel water is placed in acidic medium, the following reaction will take place. ClO minus plus Cl minus plus 2H plus produces Cl2 and H2O. Note that chlorine gas is a green toxic gas. On the label of a bottle of a commercial Jebel water, we read X degree CHL, which stands for the colorimetric degree. CHL, it is defined as the volume of a chlorine gas necessary to prepare 1 liter of hypochlorite solution at STP according to reaction 1. Hypochlorite ion, it is ClO minus. The following experiment aims at determining the colorimetric degree of the given commercial bleach. To do so, we have to follow the 3 steps mentioned below. The first step, it is the preparation of a diluted solution S. So, we prepare 100 ml of a diluted solution of Jebel water S, starting from the commercial solution. Describe the experimental procedure of the dilution, knowing that the commercial solution is diluted 5 times. So, in this step, we have dilution. 100 ml, it is the volume of the solution to be prepared, therefore it stands for V. And it should be diluted 5 times. This 5 times, it is the number of dilution times, or we can call it the number of volts. To describe the experimental procedure, we should first know how much we should withdraw from the commercial solution in order to do this dilution. So we write, according to the dilution principle, the number of moles of solute is conserved. So an initial equal and final. Therefore, the dilution factor, which is the number of dilution times, it's equal to the volume final over the volume initial. Because the number of dilution time is given, it is 5 times, and the volume final, it's also given, it's 100 times. Therefore, we can find the volume initial that should be withdrawn from the commercial solution. It will be equal to 20 ml. Therefore, we write the experimental procedure. So we put some amount of the solution S0 in 50 ml beaker in order to withdraw from this beaker the 20 ml volume. Using 20 ml volumetric pipette and pipette filler, we take 20 ml of solution S0 and then we introduce them into 100 ml volumetric flask. We add distilled water to the lime mark and then we shake to homogenize. The second step, formation of I2. We introduce into an Erlenmeyer flask the following solutions. V1, 20 ml of the diluted solution S, which is Jebel water. Some drops of starch paste solution. An excess of Ki in a solution to assure the total consumption of ClO- and some milliliters of sulfuric acid. The equation of the reaction taking place is as follows. This is reaction 3. The question is to identify the oxidant, the reductant, and the redox couples involved in this reaction. As we took before, in order to determine the oxidant, reductant, and the redox couples, we should calculate or determine the oxidation number of each element found in this reaction. So, we start by calculating the oxidation number of Cl. It is +1. The oxidation number of Cl in Cl2, it is 0. The oxidation number of I, it is -1, and that in I2, it is 0. So we can notice here a change in the oxidation number of Cl and I. The oxidation number of oxygen and hydrogen, they remain the same in the reactants and in the products. If we look at the oxidation numbers, we notice that the oxidation number of Cl, it decreases from +1 to 0, therefore Cl in ClO- undergoes reduction. Whereas the oxidation number of I-, it increases from -1 to 0, therefore it undergoes oxidation. Because Cl undergoes reduction, it is the oxidant or oxidizing agent, and I-, it is the reductant or reducing agent. Therefore, if we want to assign the couples, they are ClO-, Cl2, I2, I-. Always, as you remember, we start with the oxidizing agent and then the reducing agent. The third step, which is the final step, it is the titration of formed I2. The iodine formed in reaction 3 is titrated with a solution of thiosulfate of concentration C1 equal 0.1 mol per liter. The equivalence is reached when VE equal 10 milliliters. The question is to draw and label a schema of the setup used in this titration. So, we draw this setup. It's composed out from a stand, burette, Erlenmeyer flask. You can see in the given the concentration of thiosulfate, it is given, so this is the titrant, we place it in the burette. Whereas in the Erlenmeyer flask we are titrating I2 with unknown concentration. Number 4, write the equation of the titration reaction. If the redox couples involved, they are given their values of reducing potential E0. E0 are given, so directly we place them on the electrochemical axis. We can see that I2, it is the one having stronger oxidizing power, and S2O3 2-, it's the one having stronger reducing power. Therefore, according to gamma rule, a reaction will take place between I2 and S2O3 2-, producing S4O6 2- and I-. So, we write the half reactions, we balance them to get the overall reaction. How can the equivalence point be detected in this case? In this case, if we refer to the setup of titration, we can notice that initially we have I2 in the Erlenmeyer flask along with few drops of starch paste. So the color initially it will be dark blue. Upon the addition of S2O3 2-, it will react with I2 and I2 will change into I-. Therefore we can see that the blue color will fade out until at equivalence point it will be colorless when all I2 they are consumed. So in number 5, how can the equivalence point be detected? It can be detected by the total disappearance of dark blue color. Number 6, determine the molar concentration of I2 using reaction 4. This is reaction 4. To determine the molar concentration of I2, we apply the calculation used in titration. So we say, according to stoichiometric relation and at equivalence point, the number of moles of I2 which are present in the beaker, if they are equal to the number of moles of S2O3 2- that are added from the burette over 2. And then we replace instead of the number of moles C times V. So we will get the following. The concentration of I2 is unknown, however we have the volume that is added into the beaker along with the concentration of S2O32- and the volume equivalence. Therefore, we can get the value of the concentration of I2 that are present in the Erlenmeyer flask. Deduce the molar concentration of ClO- in the diluted Jebel water solution and deduce that of the commercial solution using reaction 3. This is reaction 3. You can see in reaction 3 we have a relation between the number of moles of ClO- and the number of moles of I2. So, according to stoichiometric relation in reaction 3, the number of moles of I2 over 1 is equal to the number of moles of ClO- over 2. However, these two species, they are present in the beaker in the same solution, so they are present in the same volume, which is 20 milliliter. Therefore, we can say that the concentration of I2 over 1 is equal to the concentration of ClO- over 2. So, the concentration of ClO- it's twice the concentration of I2, so we get 0.05 mole per liter. This is the concentration in the diluted Jebel water. To get the concentration of the commercial solution, we use the number of folds. The number of folds is equal to 5 times, therefore the concentration C0 over Cf is equal to 5, so we get the value of C0. Find the colorimetric degree of the commercial Jebel water solution. In number 8, to find the colorimetric degree of the commercial Jebel water solution, we refer to the definition of the colorimetric degree. It is the volume of the chlorine gas necessary to prepare 1 liter of hypochlorite solution at STP. This is the reaction that is involved in this definition. If we know the number of moles of ClO-, we can know the number of moles of Cl2. The stoichiometric relation between ClO- and Cl2 enables us to determine the number of moles of Cl2. We notice that the number of moles of ClO- that's equal to C times V, we can find it, which is equal to 0.25 mole. This is because the volume of hypochlorite solution, it is 1 liter. And then, using a stoichiometric ratio, we can know the number of moles of Cl2 found in this volume of solution. So after finding the number of moles, we can find the volume of chlorine gas because at STP conditions, Vm is equal to 22.4 liter per mole. Therefore, V is equal M times Vm. We apply the relation to get 5.6 liter. This is the volume of chlorine gas which is necessary to prepare 1 liter of the hypochlorite solution. Therefore, this is the colorimetric degree. And finally, explain why Jebel water should not be mixed with any household product that contains HCl, such as a flash. Simply because, according to this reaction, in an acidic medium, Jebel water will react with H+ and produce Cl2, which is a very toxic gas. So using a Chlorix along with the flash is not allowed because it will produce dangerous Cl2 gas. This PowerPoint was prepared by teacher Ali Bakri, recorded by teacher Zainab Yassin, and supervised by teacher Hiba Badawi.